Electromagnetic induction. This concept brought a revolution in electrical and mechanical industry. The concept of producing electricity through magnetism is a cornerstone in the history of electricity. So, what is this concept? How it works? Let us learn about it. The electric current passing through a wire sets up magnetic field around it, so electricity produces magnetism. The reverse case is also true. Electricity can be created through magnetism by changing the magnetic field. This phenomena of interaction between electricity and magnetism is known as electromagnetism. British scientist Michael Faraday made a great discovery on this interaction. Due to this discovery, we have DC generators, motors, and many such devices. He observed that when a bar magnet having north and south poles is suddenly brought close to a coil, an EMF or voltage is induced in that coil, which in turn makes the current to flow. So we have same setup like what Faraday had. Well, almost similar. You can see a coil connected to a bulb and galvanometer which confirms the presence of an EMF or voltage. By the way, do you know what is EMF? Let's take a quick detour. Despite its name, electromotive force is not actually a force. Electromotive force or EMF is measurement of energy that causes current to flow through a circuit. EMF is the voltage generated by source like a battery or generator. It makes the electrical charges to flow in the circuit. On the other hand, voltage can be measured across any 2 points. It can be across a battery or a resistor, but EMF cannot be measured like that. So, in the case of electromagnetism, we are calling it EMF because it is getting produced, not measured. Bottom line, all EMFs are voltages, but all voltages are not EMF. Now, let us quickly get back to electromagnetic induction. In our setup, we have a magnet having north and south pole. It is suddenly brought close to a coil and moved inside. The bulb glows and the pointer in the galvanometer deflects. When the magnet comes back, the bulb glows again, but the pointer of the galvanometer moves in the opposite direction. If you observe closely, when the magnet is stationary, there is no deflection of pointer and the bulb doesn't glow. The magnetic field lines of the bar magnet comes in contact with the coil. As the magnetic lines are continuously changing, they produce a voltage in the coil. Because of this voltage, the bulb glows and the pointer deflects. After this experiment, Michael Faraday formulated a law which we know today as Faraday's law. There are two laws. Let us now define Faraday's first law. Whenever the flux linking with the coil or circuit changes, an EMF is induced in it. As we saw in the experiment, whenever the magnet moves in and out, there is a deflection in the pointer and the bulb glows. Now, let us try defining Faraday's second law. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linkages. That is, E, being the EMF, is directly proportional to d phi by dt, which means if we move the magnet faster, the direction of the pointer and the bulb intensity will be more. This magnitude of EMF will be dependent on the number of flux lines linked with the coil. The flux linkage is given as the product of flux and number of turns in the coil, that is N phi. So, if we calculate the flux linkages over a period time, then we can write Faraday's law equation as E equals minus N d phi by dt, where E is the induced EMF, phi is flux, T is time, and N is number of turns of the coil. Here, d phi by dt represents the rate of change of flux. More the change in flux, more will be the EMF and hence the current. Negative sign is attached in the equation to indicate the fact that the direction of the induced EMF will be in the opposite direction of the cause producing it, that is the current. Until now, we saw magnet moving and coil being stationary. We can have the same effect if the coil moves and magnet remains stationary. We can replace permanent magnets with electromagnets, which is stronger and can produce more flux. Electromagnet is just a metal core having copper coils wound on it. If we pass current through this wire, the metal core will act as magnet and produce magnetic field. So, even in this case, the law holds good and change in magnetic flux linking with coil induces EMF. Without this discovery, we wouldn't have a lot of things today, all thanks to Mr. Michael Faraday. So, what have we learned in this video? The all-important electromagnetic induction and Faraday's laws. In the next video, we'll learn about different ways of producing this EMF.